Okay, I'm in a bit of a hurry. I keep getting the odd request for the second test from this year solution, so here we go. Test 2, 2017. Alright, so first question. Figure 1 shows the net force acting on a 58-gram tennis ball as a function of time. Calculate the momentum transferred to the tennis ball. Well, if you have the change in momentum is equal to the force times the time, or more specifically, it's equal to the integral of f dt for a changing force. Okay, in this case, the force increases uniformly from 0 to 100, so I think it's reasonable to assume that on the average it's 50 newtons, and the time is 20 milliseconds, so the change in momentum is going to be 50 newtons times 20 millis times 10 to the minus 3 seconds, which is 50 times 20 is 1, and 1. So the answer is B. Why did we put 58 grams in there? To trick you. It was mean. Okay. This is hard. There's a formula for it. I'm going to ignore it. There is a formula for it. Actually, no. Let's not ignore it. It's not that hard. It's actually trivial. Let's do it. So, we've got a bullet that hits a block. Alright? What we can do is we can work out, as soon as the bullet hits the block, we can use conservation of momentum to work out the speed of the block. So, initial momentum is equal to 0.005 times the velocity of the bullet, right? It's mass times velocity. So therefore, the velocity of the block is equal to what? Well, basically, we can ignore the mass of the bullet and we can simply say that 0.005 V is equal to 10 times the velocity of the block. Therefore, the velocity of the block is equal to 0.005 over 10 times V, the velocity of the bullet. Okay, now the block is suspended and it then swings up to reach a particular height. 11 degrees is the angle it makes. Okay, so what we'll have, of course, is that the initial kinetic energy of the block, 1/2 mass of the block times the velocity of the block squared, that is going to be equal to, if this is the height, it will be equal to mass of the block times g times the height. Because when the block finally gets up to its highest position, then all of its energy will be potential energy, and this will be 0. Okay, so what is the height? Well, this is 1 here, and you draw a triangle in there, 11 degrees, and interested in this height here, interested in that distance there, x, okay, and we can say h equals 1 minus x, and this length here is 1, that length there, and that little length there is x. So we can say that the cos of 11 degrees is equal to adjacent I over hypotenuse, x over 1. Okay, therefore x equals cos 11 degrees, therefore h equals 1 minus cos 11 degrees. Alright, we're getting there very slowly. So, taking that, we're going to go, alright, we're going to go 1 minus cos 11 degrees times mbg equals a half mb vb squared. Crosses, 2 goes over there, there, and so using VB is that, so 0.005 over 10 times V all squared is equal to 2 times 1 minus cos 11 degrees times G. So V squared equals 1 minus cos 11 degrees G over 0.005 over 10 squared. Realise I've got no chance of getting this right. 2 times brackets 1 minus cos 11 brackets equals, okay, times 10 equals, divide brackets 0.005 divide 10 brackets x squared equals, take the square root, and we get 1212 meters per second, or 1.2 kilometers a second. Okay, it worked. Phew. There's also just some formula, but that's how you do it. Alright, next question. The Earth moves around the Sun in an elliptical orbit where angular momentum about the Sun is conserved. Earth's distance from the Sun ranges from 0.983 astronomical units to 1.017. The AU is a unit of distance. If the orbital speed of the Earth at aphelion is v, the orbital speed at perihelion is. So angular momentum L in this case is given by mvr. Okay, so therefore we have mass is going to be the same. V at aphelion times r at aphelion is going to be mass times V at perihelion times r at perihelion. Therefore we can say that what do we want? The orbital speed at perihelion. So V at perihelion is equal to, masses cancel, RA over R P times V at aphelion. RF 1.01, so it's 1.017 over 0.983 times V. Equals 1.0345, and of those that's the closest. Alright. Okay, then the trick question. This is not a trick question. Okay, the figure, this is one, okay, you've got to read it carefully. The figure above shows a number of identical uniform boards acted on by a force shown as an arrow. The vertical component of the force is the same in all cases. Okay, so the vertical component is the same in all cases, right? If we take torques about the pivot point, there, so the correct ranking of the size of the torques produced by the force from largest to smallest is, well, we know torque is equal to the force times the distance times, and what force is it? It's the component of the force at right angles. Okay? Alright. So what's the component of force at the right angles? The vertical component of the force is the same in all cases. Okay? So the component of the force at right angles is the same in all cases. So it's easy to see that if we just look at this, we can say, look, that's halfway along, that's halfway along, that's halfway along. So D is the same for all of those, and F is the same. So those three are all the same. Here we have twice the distance. Okay, now they're all the way along, and F is the same. So these two are the same. So these two are the biggest, D and E the biggest, and then those. No. E and D, no. Hang on. Yeah, this one. E and D the same, then A, B and C the same. Okay. Cool. Where was the trick? The idea is to make you think that, hey, this one will be less because it's at more of an angle. Well, no, it's only the component at right angles that matters. Done. Alright, we've done that. In the absence of gravity, a ball of mass 2 kilograms is travelling at a constant velocity of 25 meters per second. An internal spring then forces the ball to break into two equal mass pieces, one travelling forward with a speed of 27 meters per second. There's no rotation of the ball before breaking apart, and no rotation of either piece afterwards. The change in total kinetic energy of the ball must be. Okay, well, one of the things you can say is that it has to increase. So if you were in a tearing hurry, like I am now, you would only have to choose between A and B. Why does it have to increase? Well, play it backwards. If you play it backwards, you've got two pieces of ball coming together, hitting in an inelastic collision and sticking together. You know, in any inelastic collision, energy is lost. So therefore, if you play it forwards and things split apart, well, that spring that's splitting them apart is adding the energy that would be lost in an inelastic collision if it was going the other way. So they have more energy afterwards than they had before. It's just a matter of working how much more, okay? So working how much more is really easy as well. Momentum needs to be conserved. So if initially we had the whole thing going that way at 25 meters per second, and afterwards we have one bit, half of it, going that way at 27 meters per second, then the other bit, it stands to reason, will also be going that way, but at 23 meters per second. Okay? You can work it out. The momentum here and here will be the same. But you figure if half of it speeds up by 2 meters a second, the other half must slow down by 2 meters a second. So the final energy is a half times 1 times 23 squared plus a half times 1 times 27 squared, and from that we must subtract the initial energy, a half times 2 times 25 squared. And if I do that, I'll do the whole thing with without the halves in. So 23 x squared plus 27 x squared minus brackets 2 times 25 x squared close brackets equals, and now divide by 2 for the half, and I get 4 joules. So the increase of 4 joules. That was easy. Now this is a hard one, and I actually have posted a solution for this in the Facebook group. If I get a time, I'll transfer that solution to the to LMS. But having said that, the way I did it in the Facebook group is kind of tricky, and so I'll do an attempted method of doing it here. This is the hardest question. If I had a choice and I was doing the paper, this is the one I'd leave till the end and say, no, it's too hard, I can't do it. But let's have a look. So initially we have a ball that is simply travelling along there with a speed v. Okay? It's not spinning at all. Finally, we have a ball which is, we'll make that vi, we'll make this vf, and it's travelling with vf, which will be smaller, but now it's rolling. It's rolling without slipping, which means that we have vf equals omega r, and here we have omega equals 0. Okay, So here we can say omega equals Vf over R. Yeah. Alright. Now, in terms of forces, there's only one force that's ever going to be applied. It's a force there. Alright? And that force provides both the torque to get the ball spinning, and it also provides the force which slows the ball down from its initial velocity to its final velocity. And so you would say the linear acceleration A is equal to the frictional force divided by the mass of the ball, right? And similarly, you could say the angular acceleration alpha is equal to the torque on the ball, which is F times R, the radius of the ball. This is the frictional force there, divided by the moment of inertia of the ball, which is 2/5 mr squared. Okay, so this is the linear and angular accelerations, and this is where I realise again how hard a problem it is if you do it this way. But let's just plough ahead here. So this is yeah, 5F over 2mr. That's the angular acceleration. Now, we can do the following. We can say that the change in velocity is equal to the integral of A dt is equal to integral F over m dt, and we can say that the change in angular velocity is equal to the integral of alpha dt, which is 5 over 2r, the integral of f over m dt. I kind of left it like that so that that and that are the same. Alright. Now, but we know what the change in angular velocity is. It started at 0 and finished at omega, so we can say that the final velocity over r is equal to 5 over 2r, the integral of f over m dt. Alright, because this is the change in omega, and there it is. What's the change in velocity? Well, the change in velocity is vi minus vf is equal to that, the integral of f over m dt. So vf is equal to 1 minus the integral of f over m dt. So, and this is messy because I'm running out of space. So we have, here we have Vf is equal to 5 over 2 the integral of blah blah f over m dt, and here we have Vf equals 1 minus that, and these two are the same. Yep, run out of steam. Yeah, I knew I shouldn't have done it. Okay, it's too hard. Blame Ralph. That's a hard question. Okay, let's go on to something really easy, and I'll come back to the other one if I can. Alright, so questions 7 and 8 refer to figure 2. So we have travelling waves, g of xt, a sine kx minus omega g of t, and h of x and t, a sine kx minus omega h of t plus phi. Okay, so they're two waves, they have the same value of k, they have the same value of a, so they have the same amplitude and the same wavelength. And here's a snapshot of them at a particular time. Okay, and we're told that this number here is either the same as that number or it's the opposite of it. Okay, if it's the same as it, then we have two waves travelling in the same direction. If it's the opposite of it, then we have two waves travelling in opposite directions. Okay, so use figure 2 to estimate the phase difference between these two waves at this particular time. Well, phase difference, one full wavelength from here to here, which is a distance of 12 to 24, that's so lambda equals 12 meters. So one full wavelength is 2 pi radians. The actual phase difference appears to be 2. Okay, it goes by 2, so it's 2/12, that's a fraction of a full wavelength, times 2 pi equals, and that's 2 pi is about 6, so that's 1/6, so it's about 1/6 times 6, so it's about 1, so it's C. Okay. If the waves shown in figure 2 are to form a standing wave as a function of time, certain conditions must be met. Select the statement which best describes the formation of a standing wave. Well, there's three conditions that make a standing wave. Okay, the waves must have the same amplitude, they must have the same wavelength, and they must be moving in opposite directions. And as we can see here, the condition for moving in opposite directions is that one of these is a plus and one of these is a minus, which we can only do by having those two having opposite signs. The other answers are silly. Okay, the amplitudes must be of opposite sign. The amplitude is just a magnitude, it doesn't have a sign. The wave numbers must be different. Then they'd have different wavelengths and that just wouldn't work, so that can't be right. Constructive interference when peaks in one align with peaks in the other. Well, yes, you always get constructive interference when that happens. It doesn't mean you've got a standing wave. Destructive interference when, yep, well, that will happen. That will happen when you get destructive interference with line troughs in one with peaks in the other. But if you have a look here, for example, if you consider this point here, okay, there we have destructive interference. This one is as far above as this one is below, and they add up to 0. Is that where a peak and a trough align? No. The peaks and it will be where the peaks and troughs do align in a little time, but it doesn't have to be that way. So that, yeah, okay, because it says when. In other words, it implies at a particular time, whereas this position, that's a node, it's always a node. It's always 0 there, so it doesn't need a particular time. Okay. A string of length L is fixed at both ends. In the normal description of the system, only certain wavelengths can exist on the string, and these are characterized by integers n, where n is 1, 2, 3, 4, 5, etc. Let's draw a couple. Okay, fixed at both ends. That'd be n equals 1. Let's draw again. N equals 2. N equals 3. Okay, that's enough. 1, 2, 3, drawn them. Okay, the vibration of the string is filmed after the string is set in motion. However, the field of view only allows a portion of the string of width, very small, centered on L/4 to be observed. So there's a half, there's a quarter. So we're looking at a little bit just there. On replaying the film, it is noticed that no vibration of the string is present at L/4. Okay. This implies that the only wavelengths present in the vibrating string are associated with, well, let's have a look. not L equals 1, because definitely it goes up and down there, or L equals 2, or L equals 3. No, we're actually going to have to go all the way to L equals 4, where when I draw the picture I have to divide into 4 bits, and sure enough, that bit, the window there, is a window where there will be no vibration. So n equals 4. What about if it was n equals 5 as well, or n equals 2? Well, n equals 2 we've already ruled out. N equals 5, well, you can draw it, but n equals 5 will have, it'll be slightly shorter, so it'll go through there, and by the time it gets to this point it will be vibrating again. So no, only n equals 4 works. Alright, for a spherical emitter, the wave intensity at a distance r from the emitter is represented as B over r. For B, B of r. For B of Ra over B of Rb to be equal 10 to the 5th, we need. Okay, so the intensity through conservation of energy is some constant k over r squared. Okay, so therefore B at Ra over B at Rb is equal to k over Ra squared over k over Rb squared, which is just equal to Rb squared over Ra squared. Okay, so therefore we want Rb squared over A squared equal 10 to the 5th. So therefore we want Rb over Ra equal to the square root of 10 to the 5th. However, we want Ra over Rb. So therefore Ra over Rb is equal to 1 over the square root of 10 to the 5th. 1 divide square root 1 exponent 5 equals 3.16 by 10 to the minus 3. Good, that'll do. Just have to remember, intensity goes 1 over r squared for spherical wave fronts. Alright. Alright, very straightforward Snell's law. A ray of light is instant on the surface of a transparent material and refracts as shown in the figure below. Assume the refractive index of air, this medium, to be exactly 1. What is the speed of light inside the material, where c is the speed of light in vacuum? Okay, so we have n1 sine theta 1 equals n2 sine theta 2. So therefore n2, the refractive index inside there, is equal to n1, which is 1, times sine theta 1, which is sine of 30, divided by sine theta 2, which is sine 22.46, and that is calculation sine 30 divide sine 22.46 equals 1.308, blah blah blah. Okay, so therefore the velocity, the speed of light in material 2 here is simply equal to the speed of light over 1.308 blah blah blah. So we divide this, we take 1 on x here. 1 divide answer equals 0.764. So the speed is going to be 0.764 c. Done. Okay. Now, next we have a lovely question, because it's easy. In a young slit experiment performed with green visible light of wavelength 530 nanometers, a pattern of light and dark spots are observed on a screen placed 2 meters from the slits. The centre of the dark spots are measured on the screen to lie at plus or minus 0.267, plus or minus 0.865 and plus or minus 1.765 with respect to the central axis of the apparatus. So here we have it. There's our two slits. We have the screen that is a distance 2 meters away, and we have a central bright spot there, and then we get 0.267, 0.865 and 1.765 drawn not to scale. So that's where the dark spots are. Okay, dark spots. Right. Now, estimate 1, the separation of the slits, and 2, the path difference between the rays of light that form the dark spot at minus 1.765 meters. And there is the beauty of this question, because taking the centre, there's minus 0.267, there's minus 0.865, and there's minus 1.765. Okay, what's the path difference between the two rays that reach here? It is half a wavelength, because that's what you need to get a minimum. What is it here? It's 1.5 wavelengths, because that's the next minimum. What is it here? It's 2.5 wavelengths, because that's to get a third minimum. 2.5 times 530 equals 1325. 1325. It's the only one that has got the path difference being 1325 nanometers, and that's what it has to be to produce not the first, not the second, but the third minimum. So the 2002 nanometer slit separation, yep, if you work it out, that's what you'll get. But you don't have to work it out, because these are all unique. So finding one of those, and this is a lot easier than that. Okay, down to the nice easy questions. Electricity. 2-point charges of equal magnitude and opposite sign are positioned as shown, a positive and negative. What arrow best represents the electric field at point P due to these? Okay, so positive, negative. Negative will produce a electric field towards it. Okay, there's the electric field due to Q. Positive will produce an electric field away. There's the electric field due to plus Q there. Note that this is bigger because it's closer. This produces a smaller field because it's further away. So the net field is in that direction. John Brooks. Right. Okay. So field in that direction is A. Beautiful. Done. Now here we have a picture. There's a cone. That face is horizontal. A uniform electric field of 455 newtons coulomb pointing directly up is everywhere. And they say, how much electric flux passes through the sloping sides of the cone? Well, there is no charge inside the cone. So anything which enters through the bottom face must come out through the sloping sides. We know there's no charge inside the cone because if there was, the field wouldn't be uniform. Okay? I'll leave that as an exercise for you to worry about. So all we need to do is work out how much electric flux goes through that bottom bit. Now flux, phi, is equal to electric field strength times area. In this case that's 455 naught times pi r squared, which is 455 naught times pi times I times 4.22 centimeters diameter, so 0.0211 centimeters radius squared equals 6.36. Okay, 6.36. There it is. Beautiful. And one last easy question. A charged rod is brought close to an electroscope as in the figure above. It makes contact with the conducting probe at the top and is then taken away. The two blades at the bottom of the electroscope move apart as shown in A. So here's A. We've touched the positively charged rod 2 there. These two leaves both pick up positive charges and so push each other apart. Okay. Then a second rod of negative charge is brought close to the electroscope but doesn't make contact as in B. Which best describes the process as the negatively charged rod is brought closer and the final state of the electroscope? Ooh. Okay, so we're going to bring this in closer. And now, remember here, some of the positive charge actually ran down there like that. When we bring negatively charged rod up to here, some of that positive charge will be attracted back up. And so this will be less positive, so we'd expect this to go not repelling as much and positive charge to be up there. Okay? Or we can regard it as negative charge is repelled from up here and comes down here to make this less positive. It doesn't really matter which way we look at it, but let's have a look. The second rod produces an excess of electrons which flow to the bottom of the electroscope, increasing the electrostatic repulsion and hence causing no, they're not moving further apart. The second rod induces a deficit of negative charge at the top of the electroscope which forces the blades further apart. No, they're not moving further apart. The second rod induces negative charge to be repelled from the top of the electroscope and to flow to the bottom, causing the blades to move closer together. That seems most likely so far. The second rod induces positive charge to be repelled from the top of the electroscope and to flow to the bottom, causing the blades to move closer together. Well, no. If positive charges could move, they wouldn't be repelled by a negative rod, they'd be attracted. There is no change. No, there is change. So, yep, see, look promising it is. Okay, so just going back to Ralph's horrible mechanics question. So I'm left with two things. The two things are basically, if we look at this, I'm saying, let's call this integral. Let's just call this integral, say, k, okay? I'm left with 1 minus k is equal to the same as 5 halves k. Now, and that seems a bit dodgy to me in any way, because I've treated this as positive here, so 1 minus something positive, and I've treated it as positive here, so that's fine. Yeah, okay. So if we move that k over to there, we get 1 is equal to 5 halves k plus 1 plus k. That is 1 is equal to 7 halves k. therefore K is equal to 2/7. Okay, and so V final is okay. Here I've made the mistake of assuming V initial was 1. Yep. No. I might do this separately. I can't do it for now. Needless to say, the answer was C, 5/7. Note that there were some clues here, right? 1/7 is ridiculous, loses 6/7 of its speed. That's wrong. 10/7 is ridiculous. It's going faster than it was initially. That's wrong. So it has to be between these ones. And even that looks a bit dodgy, so I'd choose between C and D if I was guessing. Okay, and at the moment I am kind of guessing. You can see that the 2/7 there and the 5/7 there look remarkably inviting, and one would be tempted to say that 1 minus 2/7 is equal to 5/7, and that should be the answer, but all I've got here is a mess at the moment. Okay.